Okay, this video we use the queuing formula for a very simple system where we have one server, one line. We will use these formulas. This is what we're going to look at. And I've already coded these up in Excel and essentially provided an Excel calculator for these numbers. So here's the problem. We've got a drive-through system. So we have one line. We only have one drive-through, so one server. And customers arrive at a rate of 15 per hour. So that's every 4 minutes they show up, 15 per hour. Now that doesn't mean that they show up exactly every 4 minutes. It's just on average 15 per hour. So we may have a whole bunch of them show up, and then we might go 20, 30 minutes and no one shows up. Just on average it's 15 per hour. And then the teller can process cars or customers at the rate of 20 per hour or every 3 minutes. So if given this 3 minutes, that means I can do 20 per hour. So we're going to assume that everything, all of our times are exponential. So let's go ahead and calculate our numbers. So this is the formulas that we need. This is all the information we need. We need to know the arrival rate, which it's 15 per hour, and the service rate is 20 per hour. That wasn't given to me, by the way. What was given to me was that they show up every 3 minutes. So how did I get that 20? How did I get this? Well, if the service time is 3 minutes, then the rate is the inverse of that. It's 1 divided by that. So that's how many people per minute. That's how many customers they can process per minute. But I'm doing this all in hours, so the rate can also be this, and I can convert this to hours by multiplying times 60 to get to a per hour. So this is, if this is given, the time is 3 minutes, then the rate in terms of customers per hour, this is customers per minute, and then I can convert that to per hour by multiplying by 60. So this was given, these are calculated, that's how this number comes up. So you know this one, you know this one, these are given. We're assuming everything's exponential. We can calculate our service times, and again, these are all in hours. These are in hours now. That's how you want to think of the same math. If that's 15 per hour, then the time between arrivals is 0.05 hours, or multiply that times 60 to get 4 minutes. So look what the utilization is. The utilization is lambda over mu. It's 15 over 20. That is 75% is the utilization. Now notice what happens if I don't have very many people show up. If the arrival rate is only 5 per hour and I can process people 20 per hour, then my utilization is really low. But what if I have a situation where I have people show up really a lot, 19 per hour, and I process people 20 per hour? You can see my utilization gets really high. And for a long-term period, this number has to be less than this number. It cannot be equal. A utilization of 100%, a lot of these formulas are undefined. So the arrival rate has to be a number. For a system to be stable, the arrival rate has to be a number that is less than the service rate. Now that doesn't mean that there's never a line, because we do have variability to this, but for the long-term stability of the system, this number has to be less than this. We calculate our utilization. Now we can calculate our performance metrics. The first one that we calculate is the average number of people waiting in line. It's about a little over 2 or 2.25 people. And again, if I play with these numbers, if the arrival rate is much less, then I don't have as many people waiting in line. If it's really high, I got a huge line. Utilization is high, I have a big line. The average number in the system, all that is, it's this number plus this number. It's the average number. All this is the total people in the system, which includes the person being served. The time, the average time in queue, remember this is in hours, so if I take that and multiply times 60, that's 9 minutes. So right now the average time waiting in queue, this doesn't include the service time, this is waiting until you get served, is 9 minutes. Look what happens when I have a real busy system. This gets way, way up there. If I don't have a very busy system, it doesn't take too long. And then the total time in system, all this is equal to this plus the actual service time. The last one is the probability of exactly n units in the system. And by far the most important one is when n is equal to 0. So n equal to 0, that's what this table over here is in this graph. What this graph is. This gives me the probability of 0 customers in the system, the probability of 1 customer in the system, 2. The probability of 0 is when the system is idle. That means there's nobody in the system. So if my utilization, well, let's get back to what the problem was. If I have people show up 15 per hour and I can process people 20 per hour, then the probability that there's no one in the system is 25%. So that means that 25% of the time when a customer shows up, he doesn't have to wait in line. And you can see as you just total these out, and that's what I have over here, this is the cumulative, you can see that I'll probably never ever get more than, rarely will I get more than 15 customers ever in my system. But it's possible, but not very. The likelihood of getting anything over that would be 1 minus this number. But look what happens when I have a real busy system. I've only got my table going out to 20, but the chances that I will have more than 20 is about 33%, because this is the probability of having 20 or less customers. So the chance of having more than 20 customers in my system is still really high. It's over 1 minus that, or 33%. So you can see that when this number, when we get a real busy system, we get really big lines. Okay, that's enough for this video. And again, all these numbers are already calculated for you. All you have to do is input these two. Thanks.